Okay, right, this tutorial is going to be about reverberation time. Very important parameter when it comes to building acoustics. Okay, so reverberation time of a room basically is defined as the time taken for the sound field to decay by 60 decibels. So in this particular case, there's a formulation to predict reverberation time, which is given by this formula here. 0.16 times V over A. In this particular formula, V is simply the volume of the space, usually expressed in terms of meter cubed, and A is a parameter which is called the absorption of the room. And the absorption of the room is basically equates to what we call area absorption, and is given by the product of alpha times S. Alpha is the absorption coefficient of the surfaces, and S is the surface area of the surfaces. Now, because a room has got multiple surfaces or surface types, we often express the absorption as the sum of alpha times S. And all that means basically is that you take on board the individual surfaces that you have in the space. So alpha 1 and S1 could be the ceiling, for example, the surface area of the ceiling and the absorption coefficient of the ceiling. Alpha 2 and S2 could be the corresponding values for the plasterboard on the walls. But you might have multiple surface types in a room. You might have 5 or 6, or you might only have 2 or 3. So you need to work out the amount of absorption in that space. So reverberation time, therefore, is a function of just really two parameters. The 0.16 is a constant, it's always fixed. The volume is important. As you can see, as you increase the volume, you will increase the reverberation time. So compare spaces such as teaching rooms to cathedral spaces. Absorption, what's the effect of absorption? If you increase absorption, the actual amount of reverberation will fall. That makes sense because the more absorption you have in the room, the less reverberant or reflective that room will be. So let's just do a one worked example that involves using this particular formula. Let's suppose that we've got a space that measures 6 by 4 meters and a height of 2.5 meters. Imagine that's your space. And let's suppose that you've been told that the average absorption coefficient of that room is 0.2. So fairly low absorption coefficients for the room. Okay, so that's the average absorption coefficients. So let's suppose that the question is that we want to work out what the corresponding reverberation time is of that space. Go back to this formula here. What we have is V and we have A. V is easy to find. V is simply the product of length times breadth times height, which we've got up here. And if we work all that out, that becomes 60 meter cubed. So that's the easy bit. What about absorption? That's the next quantity that we want. In this case, we're only given one absorption coefficient, and that's the average absorption coefficient of the room. In this instance, therefore, we just use this singular formula here. Okay, so a value of alpha would be 0.2 times the surface area of the room. Surface area of the room is fairly easy to find. We're given dimensions of the room. So all we need to do is to work out the individual surface areas of each of the walls, the floor and the ceiling. Okay, so I'm going to leave you do that, okay, outside of this tutorial. But if you work all that out, you should get a value for S of 98 meters squared. Okay, so that's basically just working out the surface area of all those surfaces. So therefore we've got now a value for 0.2 times S. 0.2 times 98 would therefore give me the absorption, and the absorption as a result of this is 19.6 meters squared. So that's the absorption in this particular room. So we're now in a position where we can use this formula here, okay, to work out the reverberation time. 0.16 times the volume, which is 60 meter cubed, divided by 19.6, which is the absorption, and that gives me a figure of we'll round it up to 0.5 seconds. 0.5 seconds is actually quite a low reverberation time. It indicates therefore that the room is quite absorptive. Okay, many rooms that we have, such as the one we're doing this tutorial in, it's got reverberation times in excess of 1 second, and some of the larger spaces, such as cathedrals, can have reverberation times up to 5-6 seconds or so. Okay, in this tutorial, we're going to look at reverberation time again. And in this particular case, we're going to look at a type of calculation involved in reverberation. So we'll do a worked example. So worked examples is a good way of illustrating how we work out reverberation time. Let's suppose that we've got a space. I'm just going to draw a table here, a very, very brief table. Okay, and what we have in this table is we have walls, we have ceiling, we have floors. So I'm going to keep this quite simple. Okay, we've got an absorption coefficient for each of those areas. The walls are at 0.3, the ceiling is at 0.5, the floor is at 0.6. So that's the absorption coefficient of the materials that make up those surfaces. This other column here is the surface area, which I shall leave blank. And this other column here is the product of alpha times S. So let's suppose the space that we've got measures 8 by 4 by 2.5 meters. So that's the actual dimensions of the space that we've got. So if that's the space that we've got, okay, let's work out the corresponding surface areas of the walls, the ceiling and the floor. 8 by 4 rooms means that the ceiling surface area is simply 8 times 4, okay, which is 32 meters squared. The floor area will be identical to the ceiling at 32 meters squared. The other surface areas we can work out from this is the surface area of the walls. We can see that we've got an 8 by 2.5 wall. We've got 2 of those. We've got a 4 by 2.5 wall. We've got 2 of those. If we work out the total surface area of the walls, we end up with a figure, I'm just looking at my notes here, of 60 meters squared. So that's the actual surface area of the walls. This product here, at this end of this table, is alpha times S. This is the actual absorption of the room. Okay, so that's the absorption. So we've got absorption to do with the walls, the absorption to do with the ceiling, and the absorption offered by the floor. So it's a product of these two parameters here. So simply these become 18, 16 and 19.2 meters squared. So all the units of those are a meter squared. What we do now is that we simply add all those up to get the total absorption in the room. The total absorption in the room as a result of that is 53.2 meters squared. So now we're in a situation, or in a position I should say, to work out the reverberation time of this particular space. All right, the volume is simply 8 by 4 by 2.5. So the volume of the space can be worked out, and it works out at 80 meter cubed. And the absorption is this calculated value here, 53.2. And if we work that out on your calculator, you'll get a figure of 0.24 seconds. Okay, so that's your reverberation time for that space. If we look at that as a parameter, that is actually a very low reverberation time. Okay, 0.24 is a fairly dead space, we refer to it, but we have got fairly high absorption coefficients for both the floor and the ceiling, and the walls are also fairly high. Typically, you'd expect something about 0.1 for hard floors, hard walls. All right, that concludes this tutorial.